let us have an application of curve fitting. So we are asked to find a polynomial that relates the periods or the time it would take a planet to revolve around the sun of the three planets that are closest to the sun to their mean distance from the sun, as shown in the table below. So we have here Mercury, Venus, and Earth, and that shows their mean distance in astronomical units and period given in years. After finding the polynomial, we are asked to test the accuracy of the fit by using the polynomial to calculate the period of Mars. But we are given already the actual values of Mars. We're just going to test the accuracy of our model through the actual values. So first, we have to find the polynomial that models or relates the periods of the three planets to their mean distance. So pause the video and try to solve this problem. Alright, so we have the following given. For Mercury, its mean distance is 0.387 with a period of 0.241. Since mean distance is given here, we're going to treat this as our x and this is our y. So therefore, our first point for Mercury will be 0.387, while its period is 0.241. For Venus, we have 0.723 for the mean distance and the period of 0.615. For Earth, it's 1, 1. Anyway, 1.000, it would be the same. So we can use these 3 points to find a polynomial that would relate the mean distance and the period. And since we're given with 3 points, the polynomial that we would need would be a polynomial of the second degree or a quadratic equation. Again, given by its general form, y is equal to ax squared plus bx plus c. So let us plug in the values. We're now going to have, from the values of Mercury, we're going to have 0.241 would be equal to a multiplied to 0.387 squared plus b times 0.387 plus c. From the value of Venus, Venus, we have 0.615 be equal to a times 0.723 squared plus b times 0.723 plus c. Then from the values of Earth, we'll have 1 is equal to a times 1 plus b times 1 times c, plus c rather. So now that we have this one, we can now set up our systems of linear equations and then have it in an augmented matrix form. So I'm going to write this already in augmented matrix form by getting the coefficients and the constants that we would have here. Thus, we're going to have the following augmented matrix. For the first row, we have 0.149769, 0.387, 1, 0.241. For the second row, we have 0.522729, 0.723, 1, 0.615. And finally, we would have 1, 1, 1, 1. So this is our augmented matrix. Now, as we can see, it's a little bit more complicated to compute this augmented matrix by hand. So, therefore, it would be very much advisable if there is a program that would be able to solve this matrix. And anyway, it's left to the viewers to be able to solve the matrix either by Gaussian or Gauss-Jordan elimination. In the previous videos, I have been using Gauss-Jordan and I will do the same here. So I'm going now to give the reduced row echelon form of the augmented matrix from the Gauss-Jordan elimination process. And I'm going to have the following matrix. I'm going to have 1 for the first row, 1 0 0, then 0.4515, rounded off to 4 decimal places, then 0 1 0, 0.6119 for the second row. Again, the constant is rounded off to 4 decimal places. Third row, 0 0 1, then negative 0.0634, again rounded off to 4 decimal places. So given the reduced row echelon form, we have now the given function would be y is approximately equal, I use that because of our rounding off, 0.4515x squared plus 0.6119x minus 0. Oops, I don't have space. Let's write that smaller. There you go. Minus 0.0634. So there. Now, we are asked to test this model using the values from Mars. Now, the values from Mars would be, let's write it down. The values for Mars would be 1.524 and 1.881. So to test if our model, our polynomial model is accurate, let's plug in the values here, which would be 1.881. Would it be equal to 0.4515 multiplied to 1.524 cube plus 0.6119 multiplied to 1.524 minus 0.0634. The right side actually adds up to 1.9187, which is a bit far to 1.881, considering they have a difference of 0.0368. Oops, sorry. Let's remove that. There you go. Difference of 0.0368. Now, this difference might be significant or insignificant, depends on the context. However, as we can see, the polynomial that we have formed does not conform with the data of Mars. So this one here does not conform with the data of Mars. However, this polynomial will conform to Mercury, Venus, and Earth, because a polynomial that fits in some points, will not necessarily fit in all the points. So in some points will not necessarily fit for all. Not necessarily fit for all. So therefore, we would know that the polynomial that we will be able to create will fit the data of Mars if we included this data point to our model. Hence, of course, if we want to have a more accurate polynomial model, we would need more data points. And that is an application of polynomial curve fitting.